Hi all, this is Xiong-Fei again, and the focus of this video will be on how the complexity of the calculator mode works. For example, now let's go down to MATHLAB Calculator here, and we see all the variety of different functions that MATLAB supports. Now let's start with some of the basic ones. Many of these algorithms are rather straightforward. Like discrete mathematics are just formulas. And the same thing with many of the probability functions. For example, let's look at the hypergeometric function. Let's just say that we have a bag of 20 marbles, and we're supposed to, and 8 of those are red. And if we draw 9 marbles out of the bag, what is the probability that we're going to draw? What is the probability that we're going to draw exactly 6 marbles? Now we're going to see that probability is rather small in this case. And we also have continuous probability distributions in addition to the discrete probability distributions that we see down here. And we also have a calculus mode. Now, the algorithm for limit function uses the limit definition of, uses a delta epsilon definition of the limit. For example, let's consider the limit as sine x over x approaches 0, and this is going to approach 1 in this situation. Now we can examine some of the other functions in here as well. For example, if we look at the derivative function, we can the derivative function actually uses the limit definition of the derivative to approximate the derivative at a point here. And if we get a function of x, for example, let's just say sine of x, and we'll approximate the derivative as 0. We'll find that derivative is 1, as we would expect, as cosine of 0 is 1. So let's just look at some of the other functions here. The second derivative function also utilizes a limit definition, and the same thing for the definite integral. For example, if we take the definite integral of, let's just say cosine x from 0 to pi over 2, we should find that definite integral is 1, as we would expect, and we can see that in this picture as well. How the definite integral function works is that it actually breaks up our function on our domain into very small subintervals, and what MATLAB does is that it'll produce very small parabolas on these intervals, and it will produce and will add up the area underneath those parabolas to find the integral. Overall, it's an approximation method, as is most of MATLAB's functions. For example, in this case, what this particular algorithm is called Simpson's rule, which is more accurate than some of our linear approximation methods, such as rectangular Riemann sums or trapezoidal sums, for that matter. And you'll see in here that most of our algorithms are numerical approximation methods rather than concrete solve functions. And this goes along with the line that MATLAB is not a computer algebra system. Rather, MATLAB is just MATLAB uses many numerical approximation techniques in order to do what we want it to do. And the same thing goes for most of these other algorithms. For example, our solve for 0 function, if we solve for the x squared minus 16 is equal to 0, we should expect, let's just add our guess of 9, we should expect our answer to be 4. And how MATLAB is going to calculate the 0 is that it actually uses an algorithm called Newton's method. For example, let me just pull that up here. This is the Wikipedia page for Newton's method, and you can see how this algorithm is going to converge on the 0 of a function. However, not in all cases does Newton's method always work. For example, let's consider the example. I would go into 2D mode here. Let's just consider. Let's just say that we have x cubed minus 2x squared plus 2. And you see here that there's a region here. Let's just say that we guess around here, and then we guess here. Newton's method is going to come here, then we're going to guess here, and then Newton's method is going to come back here, and we're going to get stuck in this infinite loop, and that never converges to the actual 0, which is over here for Newton's method. So that's why a Newton's method isn't a foolproof method for computing zeros. So the general takeaway of the gist of it is to guess wisely and not guess in a region such as over here where the algorithm will not converge. Now we can also utilize our local maximum or local minimum functions. For example, our local maximum uses the gradient ascent method, and local minimum uses the gradient descent method. And what it does is that, for example, let's go back to our graph here. What it does is that you pick a point, and then it's going to follow the derivative of that of the point along this line here, and then it'll eventually get to a point where the derivative is approximately 0, and that is where it will say the local max is. Now, same thing for the local min. It'll come down along here, and it'll converge to here. Now, however, if we aren't wise with our guesses, we might not find the local maximum or local minimum. For example, if we start our guess here, what's going to happen is that the algorithm is going to try to follow the curve along this way, and that is going to escape to infinity without converging on what we want over here. So we also have to enter our guess wisely for any of the local maximum or local minimum functions. Now, the double integral tool, it allows us to numerically approximate an integral on a complex domain. For example, let's just say that we're trying to integrate 1 on the domain x squared plus y squared is less than 1. We can leave all the other constraints here blank because we don't need every constraint for our purposes. But let's just say that we need to describe a bounding box, which is for and since we're trying to find the double integral of a area of a unit circle here, we can just describe our bounding box from -1 to 1 on both x and y. And so we can see here that we would expect the area for a unit circle to be approximately pi, and we see that is the case here. Now, what this thing does is that there's going to be a slight inaccuracy, because what the algorithm for our double and triple integrals in MATHLAB is that it actually uses a probability, a technique known as the Monte Carlo method, and to generate points that within the bounding box that fit within our constraints, and then it will actually use those points and the mean value theorem for integrals to actually guess what that integral actually is. Hence, it's not a very exact method. It has an error of about 1%, which is actually pretty big in terms of most algorithms. But however, that's one of the best algorithms we can have to analyze complex integrals on a complex domain here, and without using a computer algebra system. And the same algorithm it works for definite triple integrals. Now we can also find a gradient curl, divergence, and the Laplacian at a point, which all use limit definitions of the derivative and the second derivative. For example, let's just examine the gradient function here. Let's just say that we have a function of x squared plus y squared plus z squared, and then we have a point, let's just say is 1, 2, 3. We expect the gradient to be 2, 4, 6 here, and that's in fact what we find. So, and similar algorithms work for the curl, divergence, and Laplacian functions. And for the local maximum and local minimum functions, we find that many of that these algorithms work the same way as these algorithms do, except they work in of multiple variables rather than just in one variable. So yeah, that's basically all I have for the calculator mode. But overall though, MATLAB is actually written in Python, and this graphics interface is actually a built-in graphics module called TK-Enter, and besides that, there are no external imports or modules that are being used to do what MATLAB does. So this is how the calculator mode works, and I hope that this explains some of your frustration when you're trying to play around with MATLAB and it doesn't do precisely what you want it to do. The key here is to tell it precisely, to know the algorithms, and so that it's easier for the user to play around with all these different functions. All right, thank you.